Hi, I'm Joe James, and in this video we're going to learn how to use Python Numpy. Numpy is Python's numerical Python library, and it lets you do math functions and statistical functions. It also has a really awesome built-in multi-dimensional array data structure that it's based on. So we'll learn how to use the NUMPY array, and I'll tell you it's a lot faster than using Python lists because it's usually stored in a contiguous block of memory. So it can iterate through the items in the array much quicker, and it's also much faster to code because you don't have to write for loops. So NumPy n-dimensional arrays are sometimes also called ND arrays, and they're called this because you can have any number of dimensions. So 1 dimension or 10 dimensions or 100 dimensions if you really want. There's no limit. So to install, you can use pip install NumPy. Kind of typical way to install that. There's other ways to install if you have a package manager. Use whatever you like. And to import, we're going to do import NumPy as MP. That's the standard convention for importing NumPy. Now we're going to learn how to instantiate a NumPy array. There are a lot of different ways to create a NumPy array, and you can see all the details on the constructors here on this documents page. But I'm covering most of the most popular ones here, the ones that are going to use most commonly. So a lot of different ones here, and I got examples of every one of them. So first you can pass in a list. Here we passed in a list 1, 3, 5, 7, 9, and 11, and you can see that's in square brackets. You could also have an existing list that's assigned to a variable, and you can just pass in that variable. That will work as well. Here we print out A, and you can see we get a NumPy array 1, 3, 5, 7, 9, 11. We can also use the arange function. This is a specific function to NumPy. It's very similar, though, to the range function in Python. So there's a start, a stop, and a step. So here we set a step of 2, and we're starting from 1 to 12. The 12 is non-inclusive, so we're just getting the odd numbers from 1 to 11. So we basically get a repeat of exactly what we just did above. 1, 3, 5, 7, 9, and 11 with this arange function. But the arange function is very versatile, so you can use that very often for creating arrays of existing numbers that you want to use. So np.linspace is linear spacing. It's a controlled number of items. So the parameters are start, stop, and number of items. Instead of setting the step, you get to decide how many items you need. In this case, we're going to go from 5 to 8 in a total of 13 items. And they're all going to be equally spaced. So in this case, we get 5, 5 1/4, 5 1/2, 5 3/4, 6, and so on, all the way up to 8. So you can control linear spacing and a controlled number of items. If we want an array full of zeros, we can say np.zeros, and then we just pass in our dimensions. So 4 rows and 2 columns. So what we get is a 2-dimensional array of zeros. And if we pass in np.ones and 2, 3, what we get is a 2-dimensional array of ones. So 3 ones and 3 ones. And here you'll notice that we also set the data type. And we'll talk more about that in this video. But here we set the data type to np.int16, which is one of the defined data types of NumPy. We can pass in a number. Here we pass in 88, and we say we want an array full of the number 88. So we can pass that in, and we use np.full to do that. The array will be full of 88s, and the dimensions of the array are 6, nothing. So it's a 1-dimensional array with 6 elements. And you can see the result is 6 88s down here. If we use from string, then we can pass in a string of values, and they're separated by a space, so we have sep equals space. We also defined our data type as np.int. We didn't say what int size, but NumPy will decide that on its own. So from string will convert this, separated by spaces, convert it to integer type. And what we get back is 4 items of integer array, 25, 30, 35, 40. We can also use np.array and then pass in a 2-dimensional list. This is just a standard Python list. It's 2 dimensions. So we have 1, 3, 5 and 7, 9, 11, where there are 2 lists embedded into a list. And you see we get exactly the same type of data structure in NumPy, a two-dimensional array with 1, 3, 5 and 7, 9, 11. np.zeros like gives us something that is exactly the same shape as array A above, 1, 3, 5, 7, 9, 11. It's going to take the shape of that array and it's going to fill it with zeros. So we get a two-dimensional array full of zeros. And we assign this to B instead of A, by the way. So those are some of the constructors for NumPy arrays. Now let's look at some of the attributes. There are a number of standard attributes so that you can analyze how an array, what size, shape, and how much space and memory it takes up. A.size tells you the number of items in the array, in this case 6. A.shape tells you the shape or the dimensions of the array. So here we have a shape that's 2 by 3. Mind you, A is this. 1, 3, 5, 7, 9, 11. It's a two-dimensional array. It's 2 by 3. InDim gives you the number of dimensions. Well, we just saw the size, there are 2 dimensions. So that answer is 2. And then item size tells you how many bytes each item in the array takes up in memory. Now, every item in an array is the same data type. So they all take up the same amount of memory. So if this array is defined as int64, which is our D type or data type, int64, each item takes up 8 bytes. So item size is 8. And in bytes is the size of the whole array in memory, which in this case is 48. We have 6 items. Each item is 8 bytes. So it's 48 bytes for the entire array in memory. We could get the same value by multiplying A.size times A.item size would also give us 48. Those are some of the key attributes of NumPy arrays. You can see a complete list of attributes and methods at this link here. Let's look at indexing and slicing. We're not going to cover this in a lot of detail. There's tons of examples available online, and I don't think I need to dig into this so much. Also, I've covered this in so much detail already in using regular lists and tuples that I'm not going to cover it in so much detail here, but I'll show you a few examples. So print A, we have 1, 3, 5, 7, 9, 11. That's a two-dimensional array. And we can use an index 1 to get the 1th item, which in this case is also an array, 7, 9, 11. It's the 1th item, just the lower value here. And if we want to pass in 2 indexes, 0, 2, we use square brackets around each one of those. So 0 tells us we want to get an item out of this 0th item in this array. And 2 tells us we need to get the number 2 item in it, which is 5. So we get a 5 back, which is an integer. Another thing that's cool in NumPy is that you can slice multiple dimensions of the data by passing in multiple sets of parameters separated by a comma. So inside A, we have a square bracket for the whole array, and then we can use a colon to separate from, to, and step, or start, stop, and step for the X dimension, and then a comma, and then we can pass in start, stop, and step if we want to for the Y dimension. So we can slice rows and we can slice columns any way we want by passing in multiple parameters separated by a comma to slice the different dimensions. And here, since we take all of the items from the X dimension, and then from the Y dimension we take only column 1, because 1 to 2, the 2 is non-inclusive. So this basically says that we want the 1th column of the array, which is 3 and 9. So you can see we get back 3 and 9. There are a lot of different ways to manipulate arrays. We can reshape, we can swap axes, we can flatten the array, we can change the shape of the array, whatever we want to do. I have a few examples here, but they're covered in a lot more detail in this array manipulation routines documentation. So if we have a new range function, a range -9 to -3, and that's going to give us back a 6-element array with 1 dimension, and then we do dot reshape 2, 3 to shape it into a 2 rows and 3 columns array. So we get 9, 8, 7, 6, 5, 4. That gives us a 2-dimensional array. And then if we swap axes 0, 1, you can see that we get exactly the same values, but they're reorganized. We swap the x and y axes for the arrays. So 9, 8, and 7 is now a column. 6, 5, and 4 is also a column. And then we can flatten this back to a linear array if we want to, one-dimensional. We do c.flatten. And we get 9, 6, 8. Now the items are reorganized because of the swapping axes. But yeah, we get a flatter array now. And we mentioned dtype before. We can use data type to save space if we want. Now, in really large arrays, this is pretty important because if you have millions or tens of millions or hundreds of millions of items, the amount of space that data takes up is pretty important. So here we use, just for an example, 0 to 100. So a 100 element array, and we print the data type, which you can see is int64. Now, we didn't specify a data type. NumPy just selected that as a default, int64. So that's 8 bytes per element. And then when we look at the number of bytes of that array, we can see it's 800 bytes for the 100 elements. But if we know that we're not going to use any really large integers, 10-digit integers or anything crazy like that, we can limit this to a smaller int type. In this case, we'll pass in int8 as the data type. And then we can shrink this down to 8 bytes per item, and then the whole array only takes up 100 bytes. So if we know that we're not going to use any really large elements in the array, no more than 8 bytes, or 256, then we can define the data type to be smaller than int64. Then we can save a lot of space. What I'm saying is, use a data type that makes sense for the data that you want to store. Upcasting, rounding, print formatting. Data type of most elements is upcast to the most precise element. As I showed you up above, we're getting a lot of int64, and same thing in floating point. You'll get float 64s. So if you want to downcast those, you have to do it explicitly. So here we have e equals np.array, and then we pass in one floating point value, and then a bunch of small integers. But this data type is going to be float 64 because we have one floating point value. So when we print out e.dtype, we get float 64. So each one of these is taking up 8 bytes, and they're also all going to be floating point values. Every item in this array has to be the same data type, and in this case, we have one floating point value, so they're all floating point values. This is handy. We can round off all of the items in the array to 4 decimal places, or however many we want, in this case 4. And then we print out the array again. You can see we have all of the elements rounded off to 4 decimal places. And then if you want to set print formatting, we can set it to precision 2, or to print 2 decimal places only. And then we can also suppress scientific notation if we want by saying suppress equals true. And so this is just print formatting for NumPy arrays. And then here you can see, even though we have 4 decimal places of precision in this value, we only printed 2 of them. What kinds of data types are available in NumPy? And here you can see we use prettyprint to show the np.sc types, which is all of the available data types for NumPy arrays. You can see we have complex numbers up to 256 bits. We have floating point values from 16-bit all the way up to 128-bit precision. And we have integers from 8-bit up to 64-bit. And then there's also Boolean, objects, bytes, strings, and so on. Strings are very seldom used. You're going to see that unsigned integers, and floating point values account for most of what you do in NumPy because it's all numerical operations. So we can read and write with files in NumPy pretty easily. Actually, it's really handy to load in an entire document of text or numbers in a single line of code. So we can use the load text function, or we can use gen from text. And I put links here to their documentation. You'll find that they both are very similar. Gen from text has some fault tolerance, so that if there's a missing value or an invalid value, it can handle that. You can set, let's say, values to 0 in case they're invalid, or whatever you want to do, however you want to handle that. Load from text, your data values all have to be there. So we pass in the file name. We're going to skip the first row because in this text file, the first row is headers. And then we put our delimiter as commas, and we define our data type. And then you can see our array printed out here. And our data type prints out is int32. And then if we want to save this values, but this time we use a delimiter of semicolon instead of comma, let's say, we can put in our file name. We pass in f, which is our array name. Then we define the delimiter. And the format, we want to save these as integers. So we do %d to force it to be stored as an integer. And I want to put headers on my top of my file. So I put headers equals ABCDEFGHIJ for the name of the column headers. And then we have to put comments equals nothing, because if I don't put that, the default is for this header to have a hashtag in front of it, which makes it a comment. Now to use genFromText, the syntax is very similar. So we pass in the file name, skip header equals 1. We have one row header, so we want to skip that. Delimiter equals comma, and dtype equals int32. And you can see we loaded in exactly the same data using genFromText. So two different ways to load data. Mathematical functions are probably the most powerful and most important function of NumPy. So I really gave you a quick introduction of those here, and you're going to find a lot more information at the documentation on this page. Now the nice thing about mathematical functions is that you don't have to iterate. You don't have to use for loops to iterate through every element in your array. Nested for loops are gone. You apply one function one time to the whole array at the same time, and Python takes care of everything else behind the scenes. So if we want to print g greater than 4, Python is going to apply this comparison to every element in your NumPy array. NumPy does this for you. So you can see the result here of the comparisons for each element in the array. And if we want to multiply every item, we square it and subtract 1. Let's say g squared minus 1. We can apply that mathematical function to every single element in the array at one time, and it prints out the result here. We can also get the min, the max, the sum of the entire array, the average of the array, variance, standard deviation. These are all built-in functions that are very easy to use. So you can see the results here. And then if we want the sum of a specific axis, we can say sum of axis 1 or min of axis 0. It's pretty easy to pass in an axis as an optional parameter. And then we can get the index of an element. So the index of the min or index of the max element, or an array of indices that would put the array in a sorted order. So column operations. You can do operations on a specific row or a specific column. Pretty easy to use the row just with the square brackets and an index in it. If you want to do it on a column, we can use square brackets and then use an empty colon in the first item, and then after the comma we pass in parameters in the second one. So here's how we can define columns. This is going to be column 2 because the 3 is non-inclusive. So this gives us the second column, and we print out the max. So here we print out just the values of that column. Then we get the max by putting .max after that, and it gives us 8, which is the max of these items. And if we wanted to, we could set a pointer to that or assign it to a variable, column 3. But something you need to be aware of here is that we're not actually copying or duplicating this data. The data is still in array G. Just because we're working with column 3 now, we're still affecting the values that are stored in the G array. So when we print column 3.standard deviation, we get 2.98. And then when we say column 3 times equals 100, beware this applies to the G data. So when we print out the change in G after that multiplication there that we did to column 3, you can see that column 3, all the numbers just suddenly got bigger. So when you assign some subset of your array to a new variable like this, be aware that it may not be copying the values. It's actually just assigning a variable as a pointer to those values in the array. And lastly, let's look at NumPy random functions. So first let's set our printing options to 5 decimal places. Then we'll generate a random array of floating point values that has 6 items in it. So here you can see those 6 items of floating point values, limited to 5 precision, 5 decimal places. And we use random.randint to generate an array of integers. And here we pass in arguments from 10 to 99, and we want 8 items. So the result we get is this array of 8 items between 10 and 99. And if we just want to shuffle that array, that's array h. So we can do random.shuffle, and we pass in h. It's an in-place shuffle. So we don't need to assign the result to h again. It's already an in-place shuffle. So now we get shuffled values when we print out h again. If we want to randomly select one of those values, here we do random.choice from h, and we get 33. And then if we want to do an in-place sort, we can call h.sort. That will do an in-place sort on our NumPy array. That covers this video on NumPy arrays. I hope this introduction was helpful for you and useful, and if so, please click thumbs up and subscribe to my channel. I'm Joe James. Thanks for watching.